Hey everyone, today we are diving into differential equations. We will be learning the concepts, the core definitions, and solving methods which we need to know. First, what exactly is a differential equation? Simply put, it's an equation that involves an independent variable, a dependent variable, and the derivatives of that dependent variable. For example, look at x dy by dx plus y equals 0. It contains the derivative dy by dx. It qualifies as a differential equation. So next is the order and degree of differential equations. So the order is the highest order derivative involved, and the degree is the highest power of the highest order derivative. So it must be a polynomial equation. Yes, so that is important. So if we look at some examples, so example A is in dy by dx minus cos x equals 0. So the highest derivative is a first derivative, so order is 1, and the exponent power is 1 of dy by dx, so the degree is also 1. In example B, it is pi triple dash plus y square plus e raised to y dash equals 0. The highest derivative is a third derivative, y triple dash, right? So the order is 3. However, because of the e raised to y dash term, this is not a polynomial equation in terms of its derivatives. Therefore, the degree is not defined. Next, moving on to general versus particular solutions. So, the general solution, it will contain the arbitrary constants. So these are the solutions we get when we solve the differential equations. So there will be some arbitrary constant A, B, or C. So a particular solution gives those constants specific numerical values based on given boundary conditions. So if we take a quick example to verify this, so the differential equation is y equals e raised to minus 3x, and its solution is d square y upon dx square plus dy by dx minus 6y equals 0. This is the differential equation, and y is e minus 3x. So if we calculate the dy by dx and d square y upon dx square and substitute in it and simplify it, so we can verify that the LHS equals RHS. So it is a valid solution. So this is one simple example for the general solution and particular solution. Next are the methods of solving first order equations. So there are 3 primary methods we need to learn, or we need to practice, or we need to master. Method 1 is the variables separable. if you can group all your y terms with dy on one side and all your x terms with dx on the other, do it and then integrate both sides. The other two methods are homogeneous equations and the linear differential equations, which we'll be learning soon. This is the this is a homogeneous equation, but first we'll start with the variable separable. So this example, 1 plus y square upon 1 plus x square, that is dy by dx. So we'll take the y terms on one side and x terms on other and integrate simply. So after integration, it's tan inverse y equals tan inverse x plus c. Which is a clean solution. So next is method 2, it is homogeneous differential equation. So this happens when the algebraic function is of degree 0. To solve this, we use a standard algebraic substitution. We set the y equals vx. So differentiating this with the product rule turns dy by dx into v plus x dv upon dx. With the v term, it's dx upon dx, so it's v plus dx dv upon dx. So you substitute this into the back in the original equation, separate your new variables v and x and integrate. So that is one method to solve the first order differential equation. The third method is the linear differential equations. So the standard form is dy by dx plus py equals q. So to solve this, you calculate an integrating factor or if, which is e raised to the power of integral of p dx. Once you have an integrating factor if, the final solution follows a strict structure. Y times if equals the integral of q times if dx plus c.